Hello and welcome to our sixth and final video solution to Superquiz 1. So we're going to combine some stuff here. We got set builder notation, we got functions, and we have equivalence relation along with equivalence classes, the quotient set, transversals. We got everything going on in this problem. All right, well, let's read it carefully. F is going to denote a set. Which set? The set of all functions from the unit interval. So it says 0 to 1, which is the set of all real numbers between 0 and 1, including 0 and 1. That's right. So this is common notation. You probably saw this in your calculus course. If you use the square brackets around a pair of numbers, this means you're looking at all the numbers in between 0 and 1, including the endpoints 0 and 1. Okay, so it's there. The elements are functions from the interval 0, 1 to the set of real numbers. So these are functions whose domain is the unit interval and whose codomain is the set of real numbers. All right, and if we quickly jump down to A, right, the first thing can be completely determined right at this point. Write the definition of F in set builder notation. So let's give this a try. So we have F equals, it's a set, so we'll use the set brace. They're going to be functions. Okay, well, let's give a name to the function. And what is it going to be a name? What is it going to be? So it's going to be a subset of the unit interval cross the real numbers, right? That's what a function is. It's a subset of a Cartesian product, right? Such that, well, it should be a function. So F is a function. Okay, so now we've written it in set builder notation. Remember, in set builder notation, the first bit is the form of an element. And then the second bit is any condition or conditions. And this middle bar, right, that's the such that bar, right? That's the indicator, right? When you say such that, you mean here come the conditions. So the form of an element is that it is a subset of this Cartesian product. And what condition do we have on it? It should be a function, right? Not just a relation, but an actual function. Okay, can we do B without reading anymore? Describe all functions that are in the same equivalence class. Oh, okay, we're going to need to know what the equivalence relation is. So we haven't gotten to that yet. All right, let's go back. We define an equivalence relation R on F. Whew, okay, cool. There's an equivalence relation. Well, my goodness, you're going to define an equivalence relation on this set F. And the elements of that set F are functions from the unit interval to the real numbers. Whew. Okay, well, let's see how we're going to relate two functions to each other. So if you have two of these functions from the unit interval to the real number, so f comma g in the set F, then the pair f comma g is in the relation exactly when they have the same value at 0, or maybe you could say the same y-intercept, right? So we have two functions, and remember, they're going from 0, 1 to the real numbers, right? So basically 0 is the starting input. So we're basically saying, do they start at the same place? So if I was drawing a picture, I might say, okay, this might be f of 0 for my function. And if I have a g, and the g, okay, well, let's draw what f does. Well, maybe f does this, right, up to 1. Okay, so this would be f of 1 over here, right, f of 1. And now if I draw my g, if it starts up here at g of 0, and it does, I don't know, like that, these are not equivalent. Why? Because they're only equivalent when they start in the same place. So if I had some h, all right, that could be my h here. This could be now equals h of 0. Then f comma h would be an R. Okay, they're equivalent because they start at the same point. That's how it's defined. Okay, fine. What was the question again? Describe all functions that are in the same equivalence class as the exponential function 2 to the x. Okay, the exponential function. So if we draw the exponential function, So normally we have to draw the whole thing, right? It's going to look like that. That'd be 2 to the x. However, we only care about it when the domain is 0 to 1. So I don't need any of this stuff on the left. Okay, and actually I don't need anything past when x is equal to 1. So when x is equal to 1, I'm at height 2. When x is equal to 0, I get 2 to the 0 power, I get height 1. So I don't need anything past that. Okay, so that is 2 to the x. So I want to know what are all the functions that are in the same equivalence class as this function 2 to the x. Okay, well, the notation we use for the equivalence class of 2 to the x is we put square brackets around it. Okay, it's one possible notation, but in this class, that's what we've been using. And so the equivalence class is going to be the set of all functions in f such that 2 to the x is related to f. Okay, so we got a little set builder notation again. The equivalence class is all elements in our set which are related to this representative, 2 to the x. Now, what does it mean that they're related? Well, we go back to our definition. Our definition said that two functions were going to be related when they have the same starting value. Okay, so we're basically looking for functions. We're looking for functions that are going to start at 1, right? When their first output is 1. So this is going to be all functions such that f of 0 is equal to 2 to the 0, but 2 to the 0 is equal to 1. And that's all it is. That's what the equivalence class looks like. It's functions whose starting value is at 1. Okay, that is when you put 0 in for x, you get output of 1. All right, let's look at C. Find a, quote, convenient transversal, i.e. a set of representatives, for the equivalence classes of f. Okay, well, I guess there's a little bit of, I don't know, subjectiveness, right? What is a convenient transversal? But I'll show you one convenient one, and hopefully you're able to either get this one or something else which is similarly convenient. So what do we know about these equivalence classes, right? If you take any two elements in this, or functions in the same equivalence class, they both start at the same point, meaning at 0, they have the same output. It seems to me there's kind of an easy way to write a function that starts at any particular point, right? So if it's 0, right, let's pick some starting point, right? Like c, right? So now if my function is f of 0 is equal to c. Okay, well, what could my f be, right? I'm allowed to choose any function from the unit interval to the real numbers whose starting value is c. I'm just going to take the easiest one I can think of. I'm going to take the constant function. Right? So this goes from 0 to 1. So f of x is just the constant function c. And for any value we like, right? Any real number, I can write down a constant function equal to that real number. And if I take any two different constants, right? So if c and d are not equal but are real numbers, then if f of x is the constant function, right, c, so f is the constant function c, no matter what x I put in, and g is the constant function equal to d, no matter which x. Okay, so if both of these things are true, then f comma g is that, well, not r, but f comma g is not an f. Okay, these are not related because they don't start at the same point. F will start at c, g will start at d. Okay. On the other hand, every function in this interval has to start somewhere. So I'm hitting, by using all of the constant functions, I'm hitting exactly one function from each equivalence class. So my transversal is going to equal the set of constant functions from 0, 1 to r. Okay, so that's a convenient transversal. Just take all the constant functions. Okay, you can come up with others. Okay, it's not the only convenient one, but it's pretty convenient in the sense it's easy to understand. It's easy to see that they're all different from each other, right? That is, they're in different equivalence classes. Okay, final problem, true or false. Hey, what a way to end it. There is a bijection between the quotient set f modulo r and the set of real numbers. Ooh, so what is the quotient set? It's a good question. Well, the quotient set, that is precisely the set of equivalence classes. Okay, so let's write that down. Whoop, we went way down. Okay, so f modulo r is the set of equivalence classes of f. Okay, so it's not the transversal. That was actually taking one element from each equivalence class. Rather, the elements of this set are the equivalence classes themselves. So we want to know if there's a bijection between the quotient set and the set of real numbers. And this is where the answer to the previous problem is going to be so nice. We know that f modulo r, that's going to equal the set of all of the equivalence classes, but there's one equivalence class for each real number, right? Each constant function. So I take the set of all things of the form, take a class of C, such that C is a real number. That's what the quotient set is. And the real numbers, well, those are the real numbers, I now can build a bijection between them. So what is my bijection going to do? I'm going to take one of these equivalence classes, right? So whatever equivalence class I have, right? So let's say, in fact, let me write it like this. Let's say I just have the equivalence class of f, okay, where this is a function now, right? That's not necessarily a constant function. Where should I send it to? Well, I know that in this equivalence class there is a constant function, and it's just equal to the constant function whose value is the same as f at 0. So I just send f, the class of f, to exactly that element. All right. Now, how do I know? How do I know that this is a bijection? Right. Well, first, first question is it a function, right? And the way we would break it being a function is if two different, or rather if one different equivalence class could go to two different numbers, okay? But because we know that once you know what the function is, right? As soon as you know the function, that it doesn't matter which element in the class you take, the f of 0, or if there was a g in there, g of 0, they're all the same, then we know you're not going to two different numbers here. So this is a function. Is it injective? All right, well, how would I show if something is injective? What if I had two different equivalence classes going to the same number? So assume the class of, say, some f and the class of g both get mapped, right, to the same number. Let's call it c. Okay. Well, we know where the class of f gets mapped, right? The class of f gets mapped to f of 0. So if the class of f gets mapped to c, and the class of f is f of gets mapped, not equals, is mapped to f of 0, then f of 0 has to equal c. On the other hand, we know that the class of g would get mapped to g of 0. But it's also mapped to c. So c also has to equal g of 0. Well, that tells us that f of 0 and g of 0 are equal. But that's exactly what it means to say that f and g are in the same equivalence class. Okay, so this tells us that the map is injective, right? Or the function is injective. Okay, what last do we need? Well, we need a bijection, so we need it to be injective and surjective. So how do I get surjective? Well, this is the easy part. Surjective means for every element in the codomain, I have a preimage, right? Well, if I take an element in the codomain, which equivalence class maps to C? Well, C does. Right? You take this here is the constant function. Think of this as the constant function now, not the real number. Take the class of the constant function, right, whose with value C. Where will this be at 0? It'll be C, right? Because it's a constant function. Okay, so this implies that the function is surjective. Yay! We've got injectivity, we've got surjectivity. Combination implies that we have a bijection. And that's what we wanted to prove, yeah? Right? We wanted to show there was a bijection between the quotient set and the set of real numbers. And so the answer is true. Excellent. All right, well, there was a lot covered, but we're going to be using this stuff all throughout the semester. So if this wasn't, if all this stuff wasn't transparent, dig back in, start working on it some more, get some help. And I think if you do, then the rest of the semester is going to be a lot better. All right, we'll see you all next time.